I think this will relate you to the PC, pressed concrete. For PC girder, right? So the column is under, the anchorage is compression. Not tension, compression. Yeah. So this is a PC. So if you want to do the theory of how to evaluate existing stress in PC, I think this is Lagrangian equation of N0 there. So that's why they cannot use a frequency response to identify the nonlinear. I don't know. Yeah, I'm trying to solve this problem for a long time. Okay, if I can derive a forward analysis and I can from the deformation or what to back calculate the N0. Okay, the PC actual force. Yeah, just give me some idea. Maybe I should go home and derive. You want to do it? Because right now, a lot of PC bridge or girder, right? On site, but we don't know the current actual force. Okay? We lost the drawing. We lost the construction record, right? We don't know how to the compression stress, the PC compression stress is inside the beam. But if we can, from this solution, we do some loading tests and measure the diffraction and solve the diffraction, say we solve the N0. You see what I mean? It's possible, but it's nonlinear. So for example, if this is a solution, I do a loading test, maybe just this one. I do a loading test, Q, and I measure some displacement. I can have a lot of equations for N0, okay, and solve linear equation, and the common point, the common N0, will be the solution for the N0. Is that right? Supposedly, right? Okay, we'll solve some problem. We can try. You understand what I mean? Just like, for example, I measure W at a quarter L, W at half L, and W at 4/3 L, right? I got 3 solutions, so I plot the N0. And I plot this equation. For this equation, I got a value, right? I just try to, try different, so probably for each one have something, right? For first one, this is solution 1. For the one, and second is maybe something like this, and the third one maybe come from here. For example, the common point, this is N0. Suppose or very close. You can do many. So use the menu graphic method. Maybe you can got the common point is N0. Because this is a highly nonlinear equation for N0, right? So if I use the same P, just put there, then I have a diffraction, right? I measure the diffraction 3 points. And this should satisfy this equation. And from this solution, this is nonlinear, I just input it, right? P I know, lambda I know. Yeah, I know, right? But I don't know N0. But I can plot the nonlinear equation or the function here. And this is a solution for that equation, satisfy this equation. This is minus this equal to 0. Yeah, why not? Why not? We can try. But people usually try to use it from vibration. Difficult. I try, but it's very difficult. So now I'm thinking about using the diffraction, deformation, much better than the vibration. Why not? Write a paper, huh? Think about it. Let's publish a paper. Certainly, right? We can do but maybe combine with some vibration or some other, maybe put a strain gauge, because strain gauge is more sensitive. Once you got the diffraction, right? We can use the nonlinear, the strain theory, the bending strain, right? We can put some strain gauge and some diffraction measurement. Maybe we can solve the N0. But the problem right now is this is not you have to derive the equation for PC. We have something like offset, right? Something, right? The E value or something, right? The P is with the neutral axis will have some eccentricity, right? That will be difficult. But the idea should be the same. Use deformation, okay? And diffraction. I think the only way to evaluate the existing PC stress. Yeah. Probably you can think about it. All right? See if you have time. Do this research and publish paper. You'll be famous. It's a doctor. Doctor identified the condition of a breach. Okay, I think that's for today. And next Thursday, I will continue. So we'll have another three moment equation. I'll show you. Yeah. All right. So after this, I think we are going to do a beam with actual force on elastic foundation. Okay, with actual force, but on elastic foundation. And the governing equation with another kW into the formula, combined with actual force. So you got another equation to solve. Yeah, let's see what happens. Huh? All right, that's for today. Let's see. So understand this part? For each distributed loading Q, for the X I fixed there. So all the QX will have some contribution to my solution. And for all the loading smaller than X, this range, I am on the loading's right side, just like the case here, on the loading's right side. So this part inference function, I should use a W2. So that's why here for W2. Then for the loading larger than X, from X to L, there's all this loading. I am on the left side of this each loading. Okay? And I define the X bar from here. So this is X bar. And it will be the A here. All right? So you integrate all of this Q loading inference on me and all of the QX inference on me. That's a total diffraction caused by this distributed loading. So this is a very fundamental solution. And we use the concept of the inference coefficient. Okay. Okay. Can you answer? A little bit?
General clear.
Okay. So Monday I will give you a problem dealing with elastic foundation with this kind of loading. Open book. Yeah. Yeah, I think if you don't take this course, you never know there's something existing in the world. Huh? Some people are talking about this, but it's very. You should appreciate the idea. I learned from the book, but 50 years, 60 years ago, the guys are very smart. They solve some problems. Yeah. Okay, so I call this as classical music. Okay? You have new jazz, new wave, but this is a traditional classical mechanics, and use a lot of mathematics, okay, not computer, but the logic, the way of thinking is beautiful. You should appreciate the idea from integration, from mathematics. That's called applied mathematics. All right. Okay. That's for today. Okay. So it's Friday. Tomorrow Friday, right? Good. I like it. TGIF.